Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is minimum set. The problem difficulty is easy, and you need to know graph concept, the minimum spanning tree, and bitwise properties of XOR. Let's have a read at the problem. You are given an integer n, and with this integer n, we are going to make a set S. Now in our set S, we are going to have k pairs. This k is up to us. We can make as many pairs as we want. Now in this pair, we can have the elements a1, then the same element as b1. I mean, these two elements can be different, but you get the gist, right? We can have a1, b1, a2, b2, a3, b3, at the end ak, bk. So for ith pair, we'll have two numbers. Now these numbers have some conditions that they need to fulfill. The first condition being that the element ai has to be less than the element bi, as well as the elements have to be between 1 and m. So with this, we have our n and we have made our set S. Next up, there's one more condition. Let's assume the numbers that we are given n, we can construct any permutation. We can have n, n minus 1, n minus 3, anything that we want of our choice. Now we want this permutation to be sorted. And to sort this, what we are going to do is, we are going to pick a pair from our set that we just created. Let's say we pick x and y. What we can do is, we can swap px and py. We can do this operation as many times as we want, but we want to make sure that this permutation gets sorted after this ends. And this permutation has to be any and every permutation. So with these two fulfilling conditions, we have to make this set S, and this set S will be then called a good set. Now the cost of this set is nothing but the sum of XOR between the pairs, that is AI and BI. So for each pair, we'll do the bitwise XOR and then we'll sum it up. So for all k pairs, we'll do the XOR between them and sum it up. And that is our cost. And we need to find the minimum cost of a good set. So for input format, we have t test cases. And for each test case, we will have a single line that will contain the integer n. As for the output, we have to output a new line that will contain the minimum cost for a good set. As for constraints, number of test cases will go from 1 to 10 raised to 3, and the value of n will go from 2 to 10 raised to 9. Let's see how we can approach the solution. So from what we have seen, we have n. With this n, we construct a set S. Set S will have k sets, and these sets will have pairs, and these pairs, the elements will have to be between 1 and n, and ai has to be less than b of I. Then for every permutation that we can make of elements 1 and n, every permutation, it has to be sortable in a manner that we'll choose a pair. Let's say we choose s of I, it is x comma y. Then we can swap px with py. We can do this as many times as we want, but at the end we just want our permutation to be sorted. So let's see what is needed for us. Let's assume we have a permutation like this. We have 2, 3, 1 and 4. Now if we have this, let's say you want to sort it. So we would want to put 1 here. Let's put the correct order ones. So we would want to swap 1 at this place and we would want to swap 2 at the second place. So it will be very good for us if we have the numbers as pair of 1 and 2 so that we can swap 1 and 2 with them. So what will happen then? We will have 1, 3, 2 and 4. And it will be great if we also have a pair of 2 and 3. With this, we'll swap these two and at the end, we'll have a sorted permutation. But this can always not be the case, right? It could be that we have some other sort of pairs that give us a less cost when we do the XOR. So it would be better if you could do something like this. We could swap 3 to, let's say, at first position, and then we can swap some other. So we could also have something like this. So we have a pair of 1 and 3, right? And then once it is like this, we can have a pair of 1 and 2. So for this 2 to reach at its place, we followed something like this, right? From 1 we went the intermediary 3 and at the end we went to 2. It means there's a path between 1 and 2. And to make sure that for any and every permutation, all the numbers can move where they want, we would want our nodes. If you consider the numbers as that and a pair as edge between them, right? So we would want all the numbers to be connected. So in terms of graph, we would want a connected graph. We could have any number of nodes and would just want that we could reach one node from another. They all are connected. Now to connect them, we need to have the edges between them. Now, as I said, this k is not given anywhere in the problem. So it is up to us of how many pairs or how many edges we create. But it is in our benefit that we choose k as less as possible, because at the end we have to pay the cost, and the cost being the XOR between these two edges. So we want to have as few edges as possible and connect all the nodes. Does that sound similar? Yes. That is the minimum spanning tree problem. So we are going to build upon this. We have all the numbers and we want to have edges between them. And the edge cost is nothing but XOR between two numbers. So let's see the XOR properties. We have A, B, and we are going to XOR them. So for whenever two bits are same, they will always return 0. But if they are different, they will return 1. So this is what happens when we do XOR between two numbers. Let's see how we can use it to our benefit. So this is what we are going to do. We have the nodes numbered from 1 to n and we want to connect them and have edges between them. So let's see what we can do. We know that when we have these bits with us, if we have two bits that are not common in two of the numbers, we'll get the bit itself. But if they are common, that both the bits are set, we'll get 0. So let's see what is the minimum that we could get. Now another thing to know is that all the powers of 2 are single bit. So let's find the maximum bit of power 2 that we can have in n. So for example, if our n is 5, the largest power of 2 that we have is 2. That is 2 raised to 2 is 4, right? So what we are going to do is we are going to find that. And that will divide our set into these two numbers. We'll have 1 n minus 2k, and the other set we have is 2k till n. Now, we have two different sets and we are then going to connect them. So what is the smallest number or smallest node available in this? That would be our 2k. What is the smallest that is available in this first set? That would be 1. So 1 and 2 raised to k, both of them have mismatching bits. So if we do XOR between them, what we get is 2k plus 1. This is the answer to connect these two sets. Now, how about then connecting the elements inside these? Let's do that as well. So if we again have the same thing, 1 and n minus 2k, doesn't it look like the same what we did as earlier? It is same as 1 is to n dash, right? Some value of n. We can just perform the same thing. Pardon. Let's see the second set. What about this? What about 2k to n? Now since all the elements in this set have 2k in it, we can simply ignore it. So now this becomes 0 to n minus 2k. Now again, if we divide it into two sets, what will be the answer? Since the minimum is now 0, if we do the XOR to connect the separated sets, our answer would be just 2 raised to k. Remember, in this case, we did not have a 0, but in this case, now we do. So what we can do is, we can recursively keep on breaking our set and joining these two portions. In that case, we will have 2k plus 1 as one answer, and another would be just 2k. So with this, we'll get our answer. Now there's one more scenario where n could be equal to 2k. If that is the case, we don't have the need to solve for the second set. So we keep on solving for the set, and at the end, we'll have the minimum cost with which we can connect all the nodes that we have with as few edges as possible and keeping our cost as minimum as possible. And that will be our solution. Let's see how we can implement the solution in Python. So for each test case, we call the function solve. In solve, we take the input of n. Now once we have this n, we call the calculate function. This is the function that we are going to call recursively. Now in this function, if our L is greater than R, that is in our range, if start is greater than end, that is 1 to n, well the answer is simple, it is going to be 0. If that is not the case, and there's just a difference of 1 between them, we can simply do the XOR and return them. Next up what we are going to do is, as in our approach, we are going to find the greatest power of 2 that can have in n. Once we have that, we split the sets. The sets become 1 to 2n minus 2k and 2k to n. Now what happens if n is equal to 2k? We only need to calculate the left set. And in case n is not equal to 2k, we then calculate two sets. That would be 1 to n minus the value of 2 raised to x, and the next would be 0 to n minus x. So now with this, we keep doing this recursively, and at the end, we have the minimum cost to connect all of our nodes in our number and make it so that any permutation that we choose, it can be sorted. I hope you understood the problem, the approach, and how we can implement this in Python. Have a very good day, and I'll see you in the next video.